Hi, I'm Isarul Hassan from Department of Photonics Engineering, Chosun University. We at Laser Application Lab investigate and propose the laser frequency stabilization scheme that employs tunable modulation transfer spectroscopy to generate a dispersive like tunable locking signal that does not compromise on peak-to-peak amplitude and signal gradient. The scheme involves a relatively weak probe beam in an atomic vapor in the presence of a counter-propagating strong pump beam that is modulated by a home-built electro-optic modulator, and the pump beam frequency is tuned by an acousto-optic modulator in a double-pass configuration. The unmodulated probe beam going into the vapor cell gets modulation transfer from the pump beam by a nonlinear four-way mixing, and you can see the modulated probe beam coming out as in the figure 1. The phase modulated field on Fourier transformation can be written in terms of Bessel functions, as you can see in these equations. The offset or tuning of laser frequency is done by an AOM. The first order frequency shifted beam, as shown in figure 2, can be reflected back into the AOM for double pass configuration. And for saturated absorption, both pump and probe beam interact with the same velocity group of atoms, and the laser log just below the transition frequency of 3 to 4 D2 line of rubidium 85 atoms is shown by a red line in energy level diagram. So a laser beam coming from laser is divided into a weak probe beam and a strong pump beam by an optical window. The probe beam goes directly to the vapor cell, while the pump beam first goes to an AOM in a double pass configuration, and then it passes through an EOM, and then it is directed to the vapor cell. So figure 5 shows an SAS signal for 3 to 4 cyclic transition of rubidium 85 atoms and an MTS signal. The laser frequency is tuned by 80 megahertz, and you can see a clear line shape for locking the laser. MTS has an advantage over other saturation absorption techniques that it generates a clear line shape for cycling transitions even for closely spaced energy levels. And figure 6 shows the peak-to-peak amplitude and signal gradient at different detuning values, and you can see that the MTS signal does not compromise on both of these. So to sum this up, a Tmts signal is generated for 3 to 4 D2 resonance line of rubidium atom, and this generates a dispersive like tunable locking signal with zero background, and the peak to peak amplitude and signal gradient remains nearly unchanged throughout the tuning range, making it independent of the frequency detuning, while the SAS saturation absorption spectroscopy signals amplitude and slope changes with the frequency tuning. Thank you.